According to the valence shell electron pair repulsion theory, charge clouds repel each other to form distinctive geometric shapes. A charge cloud is the same as one lone pair or one bond. The bond can be either a single bond, double bond, or triple bond. Knowing the number of charge clouds is not important as long as you know the number of bonds and lone pairs. The number of charge clouds can be found by adding these two things up. Here are the various geometric arrangements. As you have probably noticed, you need to know the Lewis structure for the molecule whose shape you are determining. The most basic geometric shape for molecules is linear. An example of this is carbon dioxide. After figuring the Lewis structure, you see that it has two double bonds off the central atom. This molecule is nonpolar, so the bond angle is 180 degrees. There's another example of linear geometry. Xenon difluoride has two single bonds and three lone pairs around the central atom. The dipole moments will cancel and the bond angle will still be 180 degrees. The next shape is trigonal planar. A good example for this shape involves boron because it only needs 6 electrons. Other molecules will have to contain a double bond to retain this shape. Boron trifluoride has 3 single bonds and no lone pairs, causing the bond angle to be 120 degrees. The next shape is bent. An example of this is nitrite. It has 2 bonds and 1 lone pair. The lone pair causes the bond angle to be less than 120 degrees because it is more repellent than the other atoms. Another example of a molecule with bent geometry is water. It has 2 single bonds and 2 lone pairs. These 2 lone pairs cause the bond angle of water to be exactly 104.5 degrees. The next shape is tetrahedral. An example of this is methane. All nonpolar tetrahedral molecules have a bond angle of 109.5 degrees. Trigonal pyramidal is the next molecular geometry. Ammonia is an example of a molecule that exhibits this shape. It has 3 bonds and 1 lone pair. The average bond angle for this molecule is less than 109.5 degrees. Following this is trigonal bipyramidal. Phosphorus pentachloride is a molecule that shows this molecular geometry. It has 5 single bonds between the phosphorus and the chlorides. Molecules with a trigonal bipyramidal shape have 2 different bond angles. They are 120 degrees and 90 degrees. The next shape is called seesaw. It is very similar to trigonal bipyramidal, except it has 1 lone pair. This can be seen in sulfur tetrafluoride. It still has 2 bond angles, but they're both less than 90 degrees and less than 120 degrees. With molecules that have 5 charge clouds, the lone pair always goes around the middle first. Next is T-shaped molecules. This can be seen by iodine trichloride. It has 3 single bonds and 2 lone pairs. The 2 lone pairs still go around the center because it has 5 charge clouds. There's only 1 bond angle for this type of molecule, and it is less than 90 degrees. Octahedral is the next shape. Sulfur hexafluoride is an example of a molecule with an octahedral geometry. It has 6 single bonds and no lone pairs. The angle between each of the bonds is 90 degrees. The next shape, square pyramidal, is very similar to octahedral, except it has 1 lone pair. An example of this is iodine pentafluoride. It has 5 single bonds and 1 lone pair of electrons. In this case, because it has 6 charge clouds, the lone pairs start at the top and the bottom first. Because of the single lone pair of electrons, the angle between the bonds is less than 90 degrees. The final shape, square planar, can be seen by xenon tetrafluoride. This shape has 4 bonds and 2 lone pairs. The 2 lone pairs of electrons are at the top and the bottom of the molecule because it has 6 charge clouds. The bond angle is 90 degrees.